Okay, first of all, thank you so much to the conference ICSPC. This is like 13th conference on system and process control. So I will be like very thankful to present my paper over here, and myself engineer Muhammad Adnan, and I belong to basically Pakistan and currently serving at NAST, National University of Science and Technology, Islamabad right now. And today I'm going to present my article that was accepted in ICSPC conference. So my paper title is here uh, TIGWO-DLH, a chaotic distributed hybrid gray wall framework for accelerated and stable global optimization. So this paper was funded by the Ajman University, and this is all about like table content, like introduction, aim and objective, what actually I achieved, and the problem statement. After that, literature review and a comparative analysis with the existing methods and methodology, and implementation of the results, conclusion, future work, and references. So intro is all about like optimization is a like complex, high dimensional and multimodal search spaces is a challenging. Traditional deterministic algorithms like gradient descent and Newton based often fail due to local optima and computational overhead, and swarm intelligence algorithm PSO, GA, GWO offer robust alternatives for global optimization. Standard GWO suffer from parameters convergence in high dimensional landscape. Proposed DIGWO-DLH combines chaotic initialization, adaptive convergence, and distributed local learning for improved performance. This hybrid approach is highly useful for engineering problems such as localization, energy optimization, and parameter tuning in intelligent systems. So the algorithms which I have used in my paper, like GWO, Gray Wolf Optimizer, TIGWO, Tent Improved Gray Wolf Optimizer, DLH Distributed Local Heuristic Learning, and TIGWO-DLH, the proposed hybrid algorithm that was basically the combination of the TIGWO plus DLH. This one was like basic algorithm that I have implemented from removing all the like fail and the things that were not achieved in the previous existing algorithms, and HHO and Hawks optimization for comparison, and PSO and WO. These were basically the algorithm that I have used to perform my research paper. The aim was to develop a hybrid gray wolf optimization framework TIGWO-DLH to enhance convergence speed, stability, and solution accuracy in high-dimensional nonlinear and multimodal optimization problem. This will basically the aim to achieve in this paper, and objectives that I have defined to achieve this goal: integrate 10 to improved gray wolf optimizer. This will basically the algorithm that were used in the previous papers as well, but I merged this algorithm with another like DLH learning algorithm to perform to enhance the accuracy. So use chaotic initialization to increase the population diversity, and I have applied on a nonlinear adaptive convergence control to balance exploration and exploitation. So achieve the superior goal optimization performance over traditional materialistics. So this one is basically the main and problem. This paper basically addresses the problem of premature convergence and low accuracy in gray wolf optimizer when solving high dimensional nonlinear global optimization tasks. So literature review, I have studied like multiple algorithms and the papers. After reviewing all these papers, then I was able to like merge these two algorithms to get the better accuracies. So here is the like basic like chaotic GWO algorithm and using multiple chaotic maps for improved exploration. So the limitations was over here like premature um, convergence in high dimensional space persists. So the second paper that is basically all about like GWO with a 10 chaotic mapping to enhance population diversity. So what is basically the limitation in this paper, like performance unstable across the multi-modal functions. So there are multiple other papers like GWO, and here we can see the like these paper like with adaptive parameters, but here is also a like limitation for like on large scale like optimization. This fourth one is a like paper of like here like multi-strategy adaptive GWO. So here is also a like limitation over here that I studied, like complicated architecture increase computation time. So this is all, these are all basically the like 6 papers from which I got the idea to improve the accuracies. So here's a like comparative analysis from the previous existing algorithms and the right now. So this one was my like research algorithm that is given at the last. So here we can see that high dimensional performance was very high as compared to the previous existing algorithm. Here we can see, and the overall efficiency of my algorithm was like 94 to 96% over here. This was like improvement in the previous existing algorithms. So here we can see that this one was very fast on behalf of like convergence speed and stability over here, like you can see like plus minus 1.7. So it means that this is like a very like stable algorithm as compared to the previous like all existing algorithms though. So these are basically the algorithms that were performed for my research, and it's all about like methodology what actually I adopt to perform this so first one is like I developed a like chaotic initialization tent map. So this was basically the use to generate highly diverse initial population and prevents early clustering and improve global search. So the second step was to implement the like dynamic adaptive convergence control. So this was basically used to adjust these 3 parameters alpha beta gamma wolf coefficient based on like iteration feedback. And the second purpose that I have achieved by this algorithm, the balance exploration like early stage and exploitation late stage. So this was basically the performance from these 2 steps. And the third one was distributed local learning heuristic algorithm. So here we can see that this was basically the got the idea from like each wolf updates the position using local neighborhood best. So the second objective that I have achieved from this algorithm, like enhance fine tuning in multimodal and high dimensional landscapes. So the fourth one step was like multi-stage fitness evaluation. So here we can see that global fitness is it's all about like goes to optimize like local refinement fitness. After that this goes to like adaptive weighting. So this algorithm basically ensures a robust selection and prevents premature stagnation. So the fifth step that I have like implemented over here, like iterative position update TIGWO core. So the main motto of this like algorithm was to like modified encircling plus hunting equations with the nonlinear modulation. And the second objective that I have achieved from this model, like encourages deeper search around promising regions. The sixth step was like convergence and termination over here. Stop when max iteration reach our fitness threshold achieved. So this was all about like the basic structure I have performed over here to the algorithm. So this one is all about like DLH and the TIGWO parameters. So we have to combine these two basically algorithms to achieve the final and dedicated task over here. So these are basically the results over here. When I have implemented my algorithm that I was proposed, so here we can see that the finally when I embed this chaotic tent map generates diverse initial solutions like that. This was basically the back end math of this algorithm. So here we can see that there were like population size is n, problem dimension d, and iteration count t, search bounds like x min and x max. These are basically the parameters I have used over here. This algorithm basically ensures the uniform convergence and prevents premature convergence. So this is basically the graph. Here we can analyze the results of this step. After that, adaptive parameter control. So this was basically the like equation that I have used in this. So here are the like basic parameters like alpha, beta, and like we can say the sigma evolves updated non-linearly using cosine based schedule. So ensure smooth transition from global exploration to local exploitation, balance convergence speed and solution precision. So here we can see that this is basically the results of this hybrid learning position update. Here we can see that these are basically the algorithm and mathematical results, and this is basically the graphical representation of the like hybrid learning rate. Over here we can see that this is all about like learning rate that approximate like from 0.5 to 0.001. This is a like very good achievement in this algorithm test. So comparative analysis, we can see that when we apply this algorithm on sphere, so improvement after applying my algorithm so was 51%, and the last revision this was all about like 48% improvement. After that actually at this like stage we can see the 53% and 48% and 50%. Overall here we can see that observation like hybrid mechanism improves convergence and accuracy consistently. So this was all about like, and in this we have achieved like very lowest RMS. Here we can see that as compared to the other existing algorithm there were like high RMS max RMS values, but RMSE values, and here I have achieved like 0.040. This is like very lowest to stable my system as compared to the other existing results. Overall analysis was like my algorithm that was I developed like TIGWO with the DLH outperforms like as compared to like previous existing algorithms in speed, stability, and accuracy. These factors were improved with the help of my developed algorithm. That is all about like these algorithms. And chaotic initialization plus adaptive convergence, distributed local learning, that was all about like fast global convergence. So linear computational complexity like OND, highly scalable or scalable over here. Conclusion was like DIGW-DLH is like robust, accurate, and stable for global optimization as compared to the previous existing algorithm. So we got the like very low max RMSE value over here in this algorithm as compared to the previous existing algorithm. Okay, so chaotic 10 map enhances like population diversity, and DLH local learning strengthen exploration without reducing exploration. So potential application like is over here why I implemented this algorithm. So this was basically used in the like energy system. This is all about like application purpose and UAV trajectory planning. This my developed algorithm was like best fit for these applications, and as well as neural network tuning purpose. So these are basically the applications for this like. So future work is to be extend the DIGW framework with adaptive parameters control and hybrid meta heuristic strategies to improve scalability and real world optimization performance. So it means that we can go for optimization purpose with the help of like other combining factors parameters that can enhance my algorithm as well for the scalability purpose and many other things. So it's all about like reference, and thank you so much for your attention and listening me to get what actually I achieved and what I actually developed in my research over here.